Now I'm going to try and answer the other question, which is sometimes we don't necessarily just want to get a range for mu, but we might want to hypothesize that mu is equal to a certain value. Okay, and if we hypothesize that mu is equal to a certain value, what can we say? Can we say it's likely to be, or can we say it's not likely to be? Well, the very least what we can do is we can look at the data that we got and say what is the probability that we could have gotten this data if this hypothesis is true. Okay, but let me give you a very simple hypothesis. I'm going to say that I'm going to hypothesize that mu, which is my population parameter, is less than or equal to a certain number. So let's pick that number. Okay, so I have taken a certain value mu and I've hypothesized that mu is less than or equal to 210. Okay, which means my alternate hypothesis, which should be mutually exclusive and collectively exhaustive, can be that mu is greater than 210. So how did I decide 210? Well, that comes through various channels. Sometimes it comes from a business need, sometimes it comes from a research need, sometimes it comes from a benchmark that's been set up, sometimes it comes from a legal need. Okay, different real world phenomena motivate the proposing a hypothesis with different values. Okay, so what I'm going to do, and this is a general rubric for all hypothesis tests, I'm going to do two different things. One is I'm going to do some basic calculations on the data that I have. So I'm going to take the data I have, I'm going to add some numbers, I'm going to divide some numbers, I'm going to do some basic arithmetic on the data, and I'm going to create this one number that comes from doing all my arithmetic operations. I'm going to call this number the test statistic. Okay, I'm going to take this test statistic and keep it aside. So this I'm going to keep in my locker for now. Okay, now I'm going to wear my theory hat on. So first, what did I do? I put my practical hat on. Somebody came and gave me a data set. I immediately took the data set, I added numbers, divided numbers, multiplied numbers, did some of this stuff and created something called a test statistic and kept it to the side. Now I put my theory hat on and I say, if we assume that the null hypothesis is true, okay, and you make some assumptions about the distribution of various variables. You believe central limit theorem is true, you do a couple of these things, okay, then I'm going to argue theoretically that the test statistic should be no different than drawing a random number from a particular probability distribution. Okay, I'm going to repeat this. That was a lot of words, I understand. So first what you have is you got some data, you take the average of the data, you subtract some number from it, multiply some number from it. There's a reason for doing all of that. We're going to come to that. But you do all of this, and what you have left is a number. You keep that number aside. Then you reason. You reason theoretically, and you're going to see that reasoning that I'm going to do in a second. You reason that technically, if the null hypothesis is true, doing all of this should be no different than drawing a random number from a particular distribution. Okay? In the case of the z distribution, you just saw this confidence interval we did about the means, right? In this case, for instance, we're going to say that this is a z distribution, or rather, the test statistic that we have computed out here, which is a number that we have computed, should be no different than taking a random number from this distribution. So how is it? I mean, why is it? Why is it that if the null hypothesis is true, then doing these operations should result in a random number being taken from the normal 0, 1 square? Well, let's take a look. In other words, why is the z-stat a z distribution with normal 0, 1 square? Okay, we had, let's say, some original distribution. What can you tell me about the original distribution? Well, technically the original distribution does not have to be normal. I've made a normality assumption here, but we can scratch that out. So let's scratch that out. Okay, so it's some distribution, but what's its mean of this distribution? Well, it's kind of on the board, it's mu naught, right? But why is the mean of this distribution mu naught? Remember I asked you to do me a favor in saying that we have to, if we assume the null hypothesis to be true, remember we said if that null hypothesis is true. So if the null hypothesis is true, mu naught, which is, so you'll always say mu is less than or equal to some number, that less than or that number is what you call as mu naught. Okay, so here I've chosen 210 to be mu naught, but it doesn't matter, right? Nothing that I'm telling you right now changes if I change 210 to 215. It's the same concept that I'm explaining. So usually when you write out a null hypothesis, you write it out of the form mu is less than or equal to mu naught. It can be greater than or equal to, or you can say mu is equal to mu naught. Mu naught is just a way of saying some number. Okay? So now, if the null hypothesis is true, the mean can take on any value less than or equal to mu naught. What we're going to do is we're going to take the most mathematically pathological case. We're going to take the case where it's an edge condition. So we're going to take the case where mu naught is actually 210. That's the worst case, which still conforms to this hypothesis. Correct? Okay. So I've taken mu is equal to mu naught. If mu is equal to mu naught, what is the distribution of the original distribution? What is the original distribution? We don't know what shape it is. We don't care what shape it is. We know its mean must be mu naught because we're saying if the null hypothesis is true. Let us say the standard deviation is known. We're going to make that assumption that the standard deviation is known and the standard deviation is sigma. This is all true only if we know the standard deviation. Okay? Now, what is the distribution of sample means here? Normal. Okay. With what mean? Mu naught, right? So if I take a sample from this distribution and take the mean, what would the distribution of that sample mean be? Have a mean of mu naught. What would the standard deviation of that be? Sigma by square root of n. So x bar is distributed as normal mu naught comma sigma by square root of n. Everybody on the same page till now? Okay. Now what happens if I subtract mu naught from that? What distribution would I have? I take this distribution of x bar, which is normal with a mean mu naught comma sigma by square root of n. If I subtract the value mu naught from it, remember mu naught is a number. So you had a distribution mean 210, standard deviation sigma by square root of n. Now you go subtract 210. From a particular variate, you'll have another number. But from a random variable, if you're just taking a number, a fixed number away, what does it mean? It means you have another random variable, right? Now, how should the shape of that other random variable be? It will be the same shape and everything of the same. It will just move on the number line. That's all happens. So now you have this new thing. And what is this random variable? This is nothing but x bar minus mu naught. Correct? This is the distribution of x bar minus mu naught. X bar minus mu naught is distributed as normal 0 comma sigma by square root of n. Fair enough? Now it turns out if you multiply or divide a random variable, for instance this rule of subtraction that I told you, when you subtracted the mean shifts, that is not true only for normal random variables. For any random variable, you take a number and you just add or subtract a number, you're just moving that random variable on the real number line, right? Same way, if you had a random variable, and let's say, so random variable x, and let's say variance of x is a. Okay? What is the variance of k times x, where k is a constant? It's k square a, right? So if it's a standard deviation, it would have been k times a. Okay? And now because this distribution's mean is 0, the mean is not going to get shifted because of the multiplication. So if I take that x bar minus mu naught and multiply it by 1 by sigma by square root of n, or in other words, just divide it by sigma by square root of n, what should I get? Normal 0 comma 1 square. In other words, I took this distribution and multiplied. I took the variance of x. So x was the random variable. Its variance was a, or in other words, its standard deviation was square root of a. I multiplied it by 1 by sigma by square root of n. So the sigma by square root of n and sigma by square root of n got cancelled, right? And so I was left with a normal 0, 1 square. So this is nothing but the result of x bar minus mu naught by sigma by square root of n. So in other words, what I get is if I do this calculation, if I choose to do this calculation, this x bar minus mu naught by sigma by square root of n, and if I believe in the central limit theorem, if I conjecture that the null hypothesis is true, if I make a hypothesis that if it is true, then in reality, this x bar minus mu naught divided by sigma by square root of n, which is a number that I calculated and kept in the locker, should be no different than a random number taken from a normal 0, 1 squared. Now, what I can do is, I can now say, what is the likelihood? So I've gotten some number. When I did this, I got this number. Let's say I got 1.2. Let's say I got minus 1.7. Let's say I got 2.3. I got some number, right, that I stored away in the locker. Now I can pull that number out and say, what is the likelihood of seeing a number like this from this distribution? Except you already know the likelihood of a particular value from a distribution is 0. From a continuous distribution, the likelihood of you getting a particular value is 0. So we modify the statement. We say the probability of seeing a value as extreme as this, if the null hypothesis is true, that gives me the likelihood of seeing this kind of data. So I'm going to quantify the likelihood of seeing data like this by saying what is the likelihood of seeing a value as extreme as this if the null hypothesis is true. Now this is what we're going to call as the p-value. Now if this p-value is low enough, we're going to reject the null hypothesis because we are saying the probability of seeing this data, if the hypothesis is true, is so low, so maybe the hypothesis is not true. Okay? The only thing left for you to do is now to take this value. Just remember, in this step, you're not doing anything. This step is just to illustrate the logic behind what you're doing. All you're doing is you're calculating something in this step. Then you're taking this number and you'll be plugging it in out here. Okay? You're going to take the Z tables, or you're going to use Python or Excel or R or whatever it is, and say, hey, this test statistic that I calculated, what is the likelihood of this test statistic or something more extreme than this coming from this normal 0, 1 square distribution? And you're going to use that as grounds to either reject the null hypothesis or fail to reject the null hypothesis. Now, it turns out that, of course, it's in terms of truly understanding it, how you define the probability of seeing a value as extreme or more extreme really depends on how you formulated the hypothesis. So let's take an example. If, let's say, the z-stat computed to be 1.2. Take this. Okay, if the z-stat was computed to be 1.2, that's just a particular number, you might want to reason saying, so that 1.2, probability of getting a 1.2 from a normal 0, 1 square is 0, because 1.2 is a specific number. So you'll have to say, what is the probability of getting a number like 1.2 or more extreme than that? And what is extreme gets really defined by what the null hypothesis is. So for instance, if the null hypothesis is that mu is less than or equal to 210, so if this is the null hypothesis, then what would be some values of x bar which would be perfectly normal, perfectly acceptable? If you saw some x bar values that was about 25, if x bar was 25 and all your x's were 25, is that something that violates this hypothesis? So you got some values of x, you computed an x bar, and let's say that x bar was equal to 25. Does that in any way violate this hypothesis? No, right? Because mu is just supposed to be less than or equal to 210. Now, if you kept seeing values of x bar that are higher and higher and higher, let's say you saw values of x bar that were greater than 210, greater than 250, at some point, you're going to say that the likelihood of getting this x bar if the null hypothesis is true seems quite extreme. So a higher value of x bar is your cause for concern in terms of this hypothesis not being true, correct? Now, if you saw a higher value of x bar, higher and higher x bar will lead to what in your test statistic? Will it lead to an increase in your test statistic or a decrease in your test statistic? An increase, because it's x bar minus mu naught divided by sigma by square root of n. So a test statistic value that is extremely high is your benchmark for an extreme value. So when you plot this 1.2 on this, which is a normal 0, 1 squared, what you're doing is you're not only, obviously, the probability of that value is 0, you're looking at the area to the right of the curve, because those are the values of z stats that you're saying the probability of seeing something so extreme is this area under the curve. And that's your p-value. Okay? Similarly, if mu is greater than or equal to 210, you look at the other direction. And if it's two-tailed, getting values that are far away from 210, either way, are signs of the null hypothesis not being true. So you look at the area on both sides. So it will be a mirror. So if this is 1.2, this will be minus 1.2, because this is normal 0, 1 square. Okay? Okay. So just to give you a very quick, more of an applied side of this, I hope you realize that both with confidence intervals and hypothesis tests, you're really doing the same thing. You're just answering slightly different business questions, right? Using the same fundamental distribution, same essential property. For a given, they're essentially interchangeable in terms of answering certain business questions, right? So if a particular confidence interval comes at a perfect, so let's say the confidence interval around the mean is the x bar is 10 and the confidence interval is from 8 to 12. If that is a 95% confidence interval, you can make very clear statements on which values of mu is equal to something would have been rejected and would have not been rejected based on the confidence interval itself. So they're doing the same math in a sense. So we've already looked at a single thing called a one sample test. And in the one sample test, we looked at I gave you a quick idea of this thing called the z-test. But the one thing you must have noticed is that you need to know this value sigma to do the test. In many instances where you have to calculate sigma from the sample itself, we will instead be using something called the t-test, which uses s out here instead. And and just like I told you, just like you might be interested in making inferences about the mean, right? So if you were doing hypothesis tests, these are the formulas for the test statistic. If you were doing confidence intervals, the formulas to the right kind of tell you how to build an interval for the mean or whatever it is. Just like you're interested in the mean, we use the z-test when we knew sigma. We use the t-test when we did not know sigma. If you want to make an inference about the population standard deviation, you would be using the chi-square test. Now, this is different from the chi-square test of independence or chi-square goodness of fit test. Those are different tests. But if you want to make an inference, so you take a sample. That sample has some standard deviation, right? That's the standard deviation of the sample. But you are interested in the standard deviation of the population. Unfortunately, you don't have the standard deviation of the population. But with the standard deviation of the sample, can you create a confidence interval for the population standard deviation? That's essentially what the chi-square test out here tries to do. If you use the test to test the hypothesis that the population standard deviation is equal to some value, you would be doing a hypothesis test. It's the same idea. You could do this also to test proportions. Again, so think of this random variable. In this tutorial, there are 10 questions. And you have this random variable, which is the number of questions that you'll get correct as a proportion out of the 10, right? Now, if I were to take 1 or 2 or 3 of you as a sample, Each of you will reflect some proportion. I can take let's say I take the first bench 5, and I take the proportion that each of you got, and I can just say that's descriptive statistics. But I want to say something in general about the proportion of people who will answer this question either in the population or in general if I give a test like this. After watching this video, in general, what proportion of people will answer this question? So again, I have a sample proportion. Can I build a confidence interval around the true proportion, which is the number of people who will answer the questions correctly? So again, there you can build a confidence interval. So almost anything that you can think of as a random variable, where you're getting a sample from the random variable, but you want to say something about the parameter that was involved in the random variable that created this sample, you can build confidence intervals for that. And this can easily be extended to the 2 sample case, where sometimes you just don't have one sample, right? Sometimes you want to actually compare 2 samples. So you can say people who have taken this course and given this test versus people who have not. So you have 2 sets of samples and 2 populations. Again, you can hypothesize something about these 2 populations. Remember, you're not hypothesizing anything about the sample. The sample I can just compare and give you some numbers, right? But if I wanted to hypothesize something about the populations, I can say, is the mean of this population equal to the mean of this population? I'm saying each individual experiment will have a different outcome. If I take one particular question paper, the proportion of correct answers will be different from another question paper. That's the random variable. But I'm interested in comparing. So I understand that it's a distribution already. But I'm interested in comparing the mean of this distribution versus the mean of the distribution of people who did not take this course. In both cases, do I know the mean? No. In both cases, do I have a sample? Yes. In both cases, from the sample, can I compute proportions of those 2 samples? Yes. If all I do is report those 2 proportions, I'm doing descriptive statistics. But I can build a confidence interval around the difference between the 2 proportions. Right? I can create a hypothesis to see, are these 2 proportions the same? So, and you have some different variations of this. If you compare the 2 variances, it's called an F-test. And even with the t-test, you have some simple variations. Of course, when you have multiple samples, this gets extended to things like analysis of variance and the chi-square test of independence. But these are just some to give you a flavor of the scope of inferential statistics. Hopefully, just the understanding of the one sample z-test in terms of confidence intervals and hypothesis tests gives you some kind of a bedrock that there is some logic to this. If I just have 2 to 3 more minutes, one thing I want to do is give you some feel for the central limit theorem itself, right? Because we briefly spoke about it. I said you'll kind of have to believe me when I say it's true. And I'm still going to pull the same level of trickery, which is to not prove to you anything, but instead to show you that, it does actually kind of exist, and you can kind of see it in the real world. So the central limit theorem we discussed said that if you aggregate a sufficiently large number of independent random variables, the result is a random variable which is approximately normal, right? I purposefully use this term aggregate because most text definitions would be perhaps the sum of, but it turns out that you wind up using the mean more often, and the mean is nothing but the sum divided by some constant. Okay, so let's take something that is really not random, and let's see how aggregation has an effect. Okay, so let's take rolling a single fair dice. So it's fair in the sense it's not a loaded dice, it's not rigged in any way. So what is the distribution of rolling a single fair dice? First of all, is it discrete or continuous? Discrete. So is one number more likely than the other number? No. So you'll have something called a probability mass function for this. And it turns out that this is one of those f of x's, which is not a function of x at all. It's just 1 by 6. There's no x showing up in the formula anywhere. So it's a discrete distribution. If it's 1 by 6 for each of those numbers, I can kind of plot it in this graph. I've tried to plot points 1666667 or whatever. And this is the distribution. Okay. Now what I can do is I can roll the dice twice, and I can add the two numbers that come from rolling the dice, right? So what happens when I do that? First of all, can you tell me what the state space is for rolling the dice twice and adding the two numbers? It's 2 to 12, right? So it's very tempting to think it's 1 to 12, but you can't get 1. The minimum is 1 plus 1. So it's 2 through 12. Now, 2 through 12, is it equally split? And the answer is it's not, right? Because it's not equally likely, each of those outcomes. Because what are the odds that you can get a 2? The only way you can get it is by rolling a 1 on the first try and rolling a 1 on the second try. So the odds of rolling a 1 on the first try is 1 by 6. Now it's an AND condition, so you'll be multiplying. So it's 1/6, 1 by 6 times 1 by 6. So that's 1/36th of a chance of actually rolling a 2 in 2 rolls of a dice, getting a 2 after 2 rolls of a dice. Your random experiment is now rolling, catching, rolling. Think of it as that, or think of it as 2 guys rolling at the same time. I don't care, right? But this experiment, at the conclusion of this experiment, the outcome called 2 is 1/36th. Now, is it 1/36th for getting a 3? No, it's different, because now you could have gotten a 1 in the first roll and a 2 in the second roll, or gotten a 2 in the first roll and a 1 in the second roll, in which case it's 2 by 36. Now, what about 3? Is it the same 2 by 36? Just want you to think. Well, there are more ways actually. So you could get a 1 in the first roll and a 2 in the second roll and a 2 in the first roll. I'm sorry, that was for 3, right? For a 4, what is it? My mistake. It's 3 by 36 because you can get a 1 and a 3 and a 1, and a 2 and a 2. So you're already seeing a trend, right? So it's, for instance, kind of going up. But does it always just keep going up? No, at some point it starts coming down, because getting a 6 and a 6 is as less likely. So what you have is kind of like a triangle, and you can take the sum and say, I'm not interested in the sum, but I'm interested in the average. So if I'm interested in the average of rolling 2 dice, it's the same as the sum essentially, right? Except that you're dividing it by 2. In which case your state space again goes from 1 through 6. Except now you can get values like 1.5, 2.5. This 1.5 is nothing but a 3 by 2. Right? So everybody is in agreement that the same distribution we constructed for sum is what we have for average. Right? Now let's take a look at what happens when you do for 3 dice. Right? I'm not going to go through each example for this, but you can see that first it went from a rectangle to a triangle. Right? That's what happened when you went from averaging 1 dice to averaging 2 dice. You went from a rectangle to triangle. Now look, something else is happening. It's starting to get a little bit of an inflection, which is the average of 3. Now as you go to the average of 4, average of 5, and so on, you're going to start seeing even more of this change in this rectangle. The rectangle morphed to the triangle, started morphing a little bit normal, and you're going to see it morph little by little more and more normal. So one thing that you've already seen with just 2 dice and 3 dice, and you can do this on an Excel sheet. You don't need Python for it, right? So you can do this in an Excel sheet and confirm it for yourself. But the other thing that you're also seeing is, look at what's happening to the variance. Is the variance increasing or decreasing? So for the rectangle case, it was like this, 1 through 6. So this is average of 1 dice. So this is 1, this is 2, and this is 3. So what's happening to the spread? Do all of these have the same mean? The mean is not changing. You remember the distribution of sample means? The mean is still the global mean, 3.5. But what's happening to the standard deviation? It's not only changing, it's steeply coming down, right? This 3.5, which was centered at 3.5, had lots of density out here and here. Now the density on the extremes have come down, and the density in the center has gone up. The density out here has come down even more, gone up. You're seeing not only the effect of central limit theorem, where things are starting to look normal, but you're seeing the effect of the sigma by square root of n also kicking in, right? Because the standard deviation of this distribution is equal to the standard deviation of the original distribution divided by square root of 3. This would have been sigma by square root of 2. This is sigma by square root of 1, which is nothing. Ultimately, if you took infinite samples, you would have a value 3.5, and that would just be in a single location. Okay? Okay, we'll stop with that. Thanks.